Hello, welcome to our Semiconductor education program. I'm Vincent Chang. With a thorough understanding of Class A and Class B upstage, which are taught in the previous video series, we are now ready to tackle Class AB upstage. Class AB upstage, Part 1, Transfer Characteristic. So, what kind of upstage associated with this kind of waveform? Quiescent bias current ICQ, and conduction angle is greater than 180 degree. Class AB upstage. So here's the circuit diagram we're gonna analyze in this video, and then conduction angle is greater than 180 degree means on time is greater than the off time. On time is longer than the off time. So conduction angle is greater than 180 degree. So pay attention to let's turn our attention to the circuit diagram on the left. So pay attention to the bias, the VBB, base to base. So base to base. So let's review the Class AB upstage. The circuit diagram on the left and the waveform on the right. So there is a phenomenon called crossover distortion happen in the output waveform. So how to eliminate the crossover distortion? There are several ways. The first way, which I told you before, is an R-band connected the Class B upstage within a negative feedback configuration. So two keywords, high gain operational amplifier and negative feedback. So we can eliminate the dead band, eliminate the crossover distortion. All right. So within the dead band, two transistor NPN PNP cut off. So I'm going to present the second way to eliminate the dead band. So remember, within the dead band, the two transistors are cut off, right? Sleep. So they sleep. So wake up. So let's put in the battery, the 2 VBB, the VBB over 2. Half VBB to wake the transistor up, to turn on the transistor. Okay, so the concept is very simple. So when there's no signal, when VI is 0, quiescent analysis, in quiescent condition, and then the NPN is on. Why? So you have the rise. Let's assume the half VBB is 0.7 volt. So now when VI is 0, then the brown point is 0.7 volt. 0.7 volt. So 0.7 volt can turn the transistor on. All right. So also the PNP will also be turned on. And then what? The VO is 0. So up 0.7, down 0.7. So 0 up 0.7 and down 0.7. So VO equals 0. So since there's no load current, 0, right? So load current equals VO divided by RL. So load current is 0, then what? Then the IN equals IP. There's no load current, so IN equals IP. And also pay attention to the relationship between at this condition, in this situation, VI and the VO. It's kind of like the virtual short, right? VI is 0, or VO is also 0, so it's the same voltage. So which means what? Means the half VBB across the emitter-base junction of NPN, also the other half VBB can also across it can drop on the emitter-base junction of the PNP. All right. So based on the exponential relationship between IC and the VBE, you can just simply plug the half VBB into the VBE port. All right. So IS exponential VBE divided by VT. So you can get these two current. So this current is what we call the quiescent bias current, denoted by the ICQ. Q means quiescent bias current. So pay attention to the purple current on the left. With no signal input, DC bias. With no signal input. So there's a bias current called ICQ. All right. So here's the design concept. So the ICQ is the key. But who controls the ICQ? The VBB, right? So as a designer, so just imagine if you are a designer, so you need to decide what kind of VBB should be set up. So you can you can set up a VBB to control the ICQ that you want. All right, a desirable the ICQ that you want. So here's the concept. So you can ICQ can be up, right? Can goes up. So when ICQ is higher, and then what? If the ICQ is selected to be higher, then what? Then what? Now I want you to just maybe pause a little bit and quickly just draw a class AB waveform. Okay? So class AB and class A. So remember in the class AB waveform, there's the ICQ, right? So when the ICQ goes up, then what? You gradually can see the valley, right? So which means what? Remember the mountain and the valley? So means the waveform, the circuit becomes more like the 8. The circuit becomes more like the 8, more like the class A. So if you like the class A, you are the AB, but you more like the class A. Then what? You have the higher linearity. And then what price you have to pay? You have the lower efficiency. All right? So now, you can also choose, set up, the VBB you can set up not a 0.7, maybe 0.65, right? Lower. So if VBB is lower, and then what? ICQ is lower. So ICQ is lower, so imagine just AB waveform and the B waveform. So when ICQ is lower, that means what? 50-50. That means the circuit becomes more like the class B. So if you like the class B, that what price you have to pay? Distortion. So lower, poor linearity. But what gain you can get? Higher efficiency. So it's the trade-off, So class AB upstage is the trade-off between linearity and the efficiency. That's the concept you have to grasp. All right? So it's your decision. It's your call to decide what kind of level, what kind of bias you want to set up. So what kind of DC bias level you want to choose. So there's a trade-off between linearity and also the efficiency. Oh, that's the concept. Very, very important concept. So now, for the transfer characteristic, then it's very simple, right? Because up, VI up, have VBB, and down, VBN. So we can put down this relationship. So if half VBB is very close to the VBN, so these two terms got canceled out. So VO is approximately equal to VI. Okay? So it's a straight line path through origin, and then on the two end, saturation, right? The NPN and PNP got saturated. So it's very clean and simple transfer characteristic. The linear region in the middle, the saturation on both sides. And then large signal analysis. What's the basic understanding of the design concept of the class AB upstage, we are now go deeper. We are now go deeper to handle, to analyze the current relationship, okay? So now, let's start with this. Can you get this? If you can, now I want you to pause for, maybe I just give you 2 minutes. Try to figure this out. So why I put down this? To link the IN, IP, and ICQ. So which governing equation govern in any condition, in any circuit situation, then the relationship between these three currents, IN, IP, and also ICQ, quiescent bias current. Let's start with the 2 minutes break. All right, did you get it? Let me explain. If you didn't get this, then pay attention to the red zone on the left, on your left. Now, what's the relationship between the voltage? You can simply put down this, right? Right. So the voltage across these two bases. So VBB equals VBN plus VEBP. And then what? The first item, the first term, okay? So you should be very familiar with this. Why? Because VB equals VT natural log IN divided by IS. Why this? Because of this. The relationship between IC and the VB is exponential. All right? So by the same token, you got the second term, the green term. VT natural log IP divided by IS. So what about the third one? This one. So what about this one? We just taught before. So VBB equals 2 VT natural log ICQ divided by IS. Why this? Quiescent bias current. Quiescent bias current. Okay? So I said select the VBB, a suitable VBB, then they decide to get the ICQ that you want. So now, natural log A plus natural log B equals what? Natural log A times B. So we can take out the VT natural log and get this outcome. So it's a beautiful outcome. The product of the two transistor current equals a constant, a quiescent bias current ICQ squared. Okay, so it's very, very important and interesting characteristic. So here are the takeaways. The first one, design concept. So very important concept. So how to decide from the design perspective, how to design the ICQ is the trade-off. The trade-off between linearity and the efficiency. If you think the efficiency is more important to your design, then AB, but more like the B. But you think the distortion issue and linearity is more important to you, then AB, but toward more like the A. So the ICQ, the quiescent bias current level, the current level, high or lower, is the key for the trade-off. The second point, very important characteristic is the product between these two currents at all time. Okay, so just imagine the waveform. It's a constant. So what is the constant? The ICQ square. So which means when IN goes up, IP goes down. Right? So imagine there's a two waveform. Okay, so IN goes up. If IN goes up, IP will goes down. If IP goes down, IN will goes up. If NPN conducts stronger, and then the PNP gets weaker. When PNP gets weaker, and when NPN gets weaker, then PNP gets stronger. You know what I'm thinking about? I'm thinking about a relationship between man and woman. So even you are in a dating relationship or in marriage, especially in the marriage, when a wife gets weaker, the husband should be stronger. When husband kind of fall and stumble, then the wife have to be strong. So this is same thing, the truth in life. Very interesting. So I'm happy to share with you this today and hope you receive something from this video. Thank you very much.